Natalia didn't see what happened yesterday. We had a pointer that somehow or other became disconnected from this universe for a while. It had a life of its own. Well, thank you to the organisers for inviting me to speak this morning. I'm going to try and say a few things about the thermodynamic constraints of physical learning machines. I'll explain what I mean by that in both the classical and the quantum setting. So I think I can use this to advance it. Yes. So the way I'd like to start this talk is by suggesting that there's a very common framework to think about quantum computing and machine learning. And one of the key lessons of machine learning as it's currently being developed is that it provides a completely new paradigm for thinking about what it means to do computation in terms of learning and constructing functions through training. The key point about AI and quantum computing is that they basically concern themselves with algorithms for transforming probability distributions over data, and they both require specialized hardware to run. At least in the case of classical machine learning, the hardware is not specialized enough at the moment, in my opinion. It's fixated on CMOS devices and digital computing, and this will ultimately be hopeless for energetic reasons, but there are lots of other ideas out there for moving beyond CMOS devices and digital computing for machine learning in terms of analog and spiking neural networks. But that's another story. I just want to focus on this common way of thinking of computation as transformation of probability distributions. Okay, so in machine learning, the objective is to learn structures and uncertainty. By structures, I mean very complex correlations embedded in high-dimensional data by modifying or mapping simpler initial distribution sets to match the complex patterns. That's essentially what happens in machine learning. In other words, they necessarily compress information, which means, of course, there has to be a reduction in entropy, and therefore it's no surprise that these machines take a vast amount of energy to run because they are producing a huge reduction in entropy in terms of the functions that are being learned. So I want to distinguish between deep learning algorithms. The way it's done at the moment is based on essentially taking a mid-20th century misunderstanding of the way the brain works and writing it into codes and simulating it on digital computers as these deep learning neural networks. But what I'm mostly interested in is not algorithms, but actual machines that do the learning or the computation, if you want to think of it that way. So we're quite accustomed to universal classical probability sampling using transistor circuits. This is how it's done in machine learning. Most of us grew up thinking of computation as an entirely deterministic process, but in the modern era with machine learning, it's far better to think of it as a non-deterministic process. But basically, they all work like this. There's some clock signal going in at the top, and there's a synchronized array of cascaded switches, typically MOSFETs of one sort or another. And then there are these strings of binary encoded voltage spikes that run into these circuits and cause a sort of dominoes to fall in a synchronized way, all locked to some clock signal. But the point is, it's always binary digits in and binary digits out. Perfectly classical, could be highly stochastic in a neuromorphic device, but in a CMOS device, it's quite deterministic. Unless, of course, you want to simulate non-deterministic processes with Monte Carlo methods. This is what you do for the quantum case. Everything stays the same on the outside. You just replace the box. And of course, when I say just replace, that turns out to be quite a significant engineering difficulty. But one thing is for sure, it's classical signals in and classical signals out. Of course, you don't have to have classical signals out. You don't have to measure the output for the quantum computer. But if you don't measure the output from the quantum computer, you quite literally have done nothing in terms of computation. You've just spent a hell of a lot of energy switching various devices on and off inside this box. So from this point of view, the key distinction between a quantum and classical computation, realized as probability sampling, is that in the case of a quantum computer, they transform probabilities of bit strings all right, but they do it by transforming probability amplitude to a deeper level. The probability distributions that you sample are constructed using the Born rule. So computation in this picture is like the controlled interference of probability amplitudes on a massive scale. And the algorithms that we've devised in quantum computing exploit this to achieve more efficient transformations of probability distributions than you could achieve in a classical computer. Even better, the class of probability distributions that you can reach in the quantum case is vastly different from what you can reach in the classical case, because we know that in the quantum case there are unusual correlation functions like GHZ and Bell violations and so on, and all the way up to 2 to the n qubits that can't be simulated efficiently with classical Monte Carlo. So in quantum mechanics, as everybody knows, probability is not primary. We need probability amplitudes. And here's an example in optics of what I like to call the Large Boson Collider, which is a linear optical network of the kind being pursued by PsiQuantum and QCore and Quandela and lots of other places, which basically take single photon states at the input, which are highly non-classical pulse states, which contain one and only one photon per pulse. Well, you don't have to restrict it to one, but typically it's one. And then pass it through an optical interferometer with many paths, and then count photons at the end. And your objective is, given the reflectivity and transmittivity of all these fiber couplers, compute the probability distribution for photon number measurements at the end. And the linear optical constraint tells you that the sum of the total number of photons going in and coming out, if there's no loss, cannot change. So the objective in building a quantum computer, well, not so much a quantum computer, but a quantum probability sampler along these lines, is to find ways to generate these amplitudes, the probability amplitude to count this particular integer string, n1, n2, n3, n4, n5, and n6. The probability amplitude to calculate that conditioned on a given input. And that, of course, is very difficult. It was noted long ago by Aronson and Arkhipov that to do that required computing the permanent of an n by n matrix, and as a mere physicist, I had no idea that was computationally difficult. I wish I'd done a course in computer science long before I got involved with linear optics, because it turns out that is sharp P complete. It's not universal for quantum computation. To make it universal for quantum computation, you need to have some extra nonlinear control operations, and they turn out to be photon counting plus feed forward or feedback. That's one way to do it. Or you could put Kerr nonlinearities inside the interferometer. That would also be universal for quantum computation. But the point I want to make is that it's a way of transforming probability distributions on integers in an entirely quantum mechanical way. Now, that's not the way we tend to think about quantum computation today, because quantum computation has been built on the paradigm of digital computation, which is all based on binary strings and gates and circuits. So very early on in the history of quantum computing, people figured out a universal engineering protocol, a combinatorial protocol, for generating arbitrary distributions on binary strings, and that was an analog of classical Boolean circuit design. And it's based on discretizing time, or so-called trotterizing, and representing the total transformation of input probability amplitude to output probability amplitude. There's a discrete set of unitary operations on 1 and 2 qubits at a time, maybe 3 qubits at a time. And this led to where we are today, perhaps unnecessarily slavishly dedicated to qubits, gates, and circuits for doing quantum computation. But of course, you don't get anything done at all unless you measure the output. Typically, we always initialize the input by some sort of quench or cooling operation, and then we run it through this sequence of, it's an incredibly time-dependent Hamiltonian that's going on here. You can think of these as passing through single qubit potentials with controlled collisions between the qubits to do the 2 qubit gates. But at the end of the day, you have to actually make single qubit measurements, usually in the computational basis. So the key point to emphasize here is, without that final step of measurement, nothing is actually computed, and that is where irreversibility enters in an essential way. Of course, the other place irreversibility enters is in state preparation, and that's usually done by cooling. Okay. So in this case, what's normally regarded as the so-called sign problem, by which condensed matter physicists and particle physicists simply mean that to determine probabilities, you need to determine probability amplitudes. And probability amplitudes are not necessarily positive. In fact, they're not necessarily real. But in quantum computing, the sign problem is not a bug. It's actually a feature. It's the key point. And it can generate a new class of probability distributions over binary strings more efficiently. And you say, well, so what? Well, we know that there are nice algorithms, for example, Shor's algorithm and eigensolving problems, for which this particular trick gives you a speed up. Okay, so now I want to switch from that sort of brief and perhaps somewhat eclectic approach to quantum and classical computing to talk about quantum and classical physical learning machines. So now I don't want to talk about algorithms. I want to talk about actual machines that learn. Now, the whole idea of a machine learning algorithm goes back to the middle of the last century when people like Rosenblatt and so on developed this idea of a perceptron, and essentially it uses a nonlinear activation function, which is, in this case, a sigmoidal function of the input, and the input is a weighted sum over lots of data points, x1, x2, x3, and x4, with weights chosen according, well, initially they're chosen completely random, but they're modified as the computation proceeds in a way I'll explain in a minute. And so these run into the activation function, which then can switch from low to high or high to low, depending on which way around it's going. And that is the key computational element in algorithmic learning machines. Networks of those things we now know can be used to represent arbitrarily complicated functions of many variables. And the key point is that this activation function is nonlinear, and so this linear sum of the data is turned into extremely high order functions of products of x's, xi's, and xj's. So I don't mean that. What I mean is replacing that with a physical device that does something similar. We have a bunch of incoming signals, perhaps binary time series of ones and zeros, maybe just an analog signal from speech or pixels in an image. These are then run through amplifiers or de-amplifiers, which essentially produce a weighted sum of the signals. So these could be, for example, parametric amplifiers or phase-independent amplifiers or anything at all. And then they run into a sum, something like an XY mixer, and this now runs into a switch, a nonlinear device, the output of which depends upon the value of the physical signal here. This is a nonlinear and highly dissipative device. Why is it highly dissipative? When it switches, you don't want it bouncing backwards and forwards from 0 to 1 before it finally settles into a particular output pattern. That would make it far too noisy. So you make it highly dissipative so that it locks onto 0 and 1. So that means it has to dissipate heat, and you need work to make it function. But the way to make it a learning machine is I take, in the case of supervised learning, take my signals and attach a label to it. If these are pixels corresponding to a cat, it should say that's a cat. And then I compare the output in this simple discriminator fashion with the label, and then run it through a comparator and produce an error signal, which I then feed back onto the weights, or the amplifiers and the parametric amplifiers and so on. And I build up very large networks of these things. And so from this point of view, machine learning, this physical machine learning, is an aspect of classical stochastic control theory. There's a very close link between classical stochastic control theory and machine learning, which is being exploited more and more in the machine learning community. So, this is my favorite parable for illustrating why learning necessarily dissipates heat. Imagine we have some farmer up there near the Pyrenees who has goats and sheep, and for some bizarre reason they're very hard to distinguish one from the other, or perhaps farmers, a bit incompetent and can't tell a goat from a sheep. So they decide to build a machine full of gates and pulleys and ramps and all sorts of things that open and close, and they randomly send in goats and sheep, and initially they come out in either one or the other output channel. One output channel is labeled goat, and the other output channel is labeled sheep, and initially they come out at completely random. But then the engineer designing this sits down here looking at every time it makes a mistake, in other words, sends a goat out in the sheep channel or vice versa, goes back and pushes on a lever, changes the tension in a gate, lifts up a ramp, lowers the ramp, all entirely irreversibly so that it doesn't flop around all over the place. And you keep doing this over and over again, and it's pretty obvious that this is dramatically reducing the entropy from 1 bit, 50-50 up here, to a much smaller number, determined entirely by the error probability at the output. Seen this way, of course, is just a Maxwell demon, but running in this kind of irreversible feedback fashion. So clearly the entropy has changed. As I've tried to emphasize, the device is a physical device which is highly irreversible and therefore necessarily dissipates heat. Heat and entropy must be dissipated during training, and the objective is, as I'll show in a minute, once it's trained, the minimum amount of heat should be generated during inference. So here's a simple model, goes back to Landau. We imagine a double well potential, so this Vx in here, I should have written it down, is a quartic potential with two symmetric double wells. And we put on some weights by a linear bias, and I'll assume it's extremely overdamped so that I don't need to use more than one single variable, the position of the particle. The reason why you would like it to be overdamped is if I have a double well and I'm wiggling around the bias, I don't want it to go into endless oscillations. I want it to move smoothly from one well to the other. And so I put in lots of damping. The fluctuation dissipation tells you that if there is damping, there is necessarily noise. You can't do anything about that. In fact, that is a feature. It can only learn with a required element of noise. And so this is a stochastic differential equation, or actually written in this form, it's a Langevin equation. And this is the corresponding Fokker-Planck equation, where you see there's a diffusion term in momentum coming from this double derivative with x. And this could be a highly nonlinear systematic part. And beta is this key parameter. It's the mass times the friction, gamma, the rate of dissipation. Whoops, no, I need this thing. So here's an example of how it works. Imagine we start off with the particle on the left, and we slowly change the bias to move it to the right. In the steady state, the probability distribution is easily found because it's only one dimension, satisfies potential conditions. In this case, it's most likely to be found on the left. If this case is most likely to be found on the right. I stress that's the steady state distribution. What you actually see in a given run, I'll come back to that, is a stochastic signal where here I'm imagining I vary the bias from -20 to +20, so I have it totally biased in one well and I go through equal bias and then biased in the other well. And you see if I started in one well, there is stochastic switching. Not all of them switch. This is 5 trajectories. Some of them switch and some of them don't. Here, though, they tend to switch at one particular value of the bias. It's plotted as a function of time because the bias is a function of time. I just choose a linear ramp for the bias. So as the noise is decreased, of course, the switch becomes slower and slower and slower, because if there's hardly any noise, I've got to change the bias almost completely for it to switch. It's never going to jump at some partial bias setting. So that means if I go back and look at the average position of the particle as a function of the bias and at different levels of noise, I get something which is not very well localized as a switch. As I decrease the noise, it switches more and more sharply for a particular value of the bias. So these are the sorts of pictures you tend to see for sigmoidal type machine learning. From this stochastic picture, these represent average values of the output of the neuron. What you actually see, or the perceptron, what you actually see are these stochastic signals, and you need to sample those by running it many, many times in what's called a training epoch. Okay, so key lesson is dissipation and noise are essential for efficient learning machines. Everybody knows this, the old saying, if you never make a mistake, you never learn anything, because you never need to. And if you only make mistakes, you never learn anything either, but you probably don't have much of a future. So it's sort of obvious in retrospect that without noise, you can't learn. Now, in this case, we can start thinking of how to use stochastic thermodynamics to describe what's going on. This is the best way to understand the energetics of these switching devices. So we can ask, how does Jarzynski's equality work in this setting? So remember, we're changing the bias as a function of time. We're doing work on the system, but at some random time, it will switch from one world to the other. And so the work done is a random variable, and we know from Jarzynski's equality, we can equate the average value of this exponential function of the work done over many trials to the change in the free energy. In the case I'm considering here, I'm going from one bias to an identical bias in the other direction, so the entropy won't change in the steady state, and neither does the energy of the system change in the steady state. So the free energy change in this perfectly symmetric case is 0, and sure enough, if you do a simulation of many trials, you can show that the change in the free energy is pretty close to 0, and you both do and you do work on the system, and the system does work on you in equal amounts as you change from one side of the bias to the other. Okay, so that's all classical. A classical physical perceptron is a dissipative switch subject to thermal noise. Too much noise, learning rate goes to 0. It's just random number generator in that case. And too little noise, the learning rate goes to 0 as well. So now I want to switch to the case of a quantum perceptron. And this will be a universal physical emulation. And I want it to be a dissipative switch, just like the classical case. You might be wondering, whoa, shouldn't it be coherent if it's going to be quantum? We'll come back to that. It's subject to quantum noise. And again, too much noise, learning rate goes to 0. Too little noise, learning rate goes to 0. What do I mean by quantum noise? I mean quantum tunneling, spontaneous emission, etc., etc., etc. And all of these things take place at 0 temperature, and all necessarily assume entanglement between the local system and the environment. That's how spontaneous emission arises. It's because when you quench the system, you prepare it in a non-stationary state, which is a highly entangled state of the local degrees of freedom and the environmental degrees of freedom, which we trace over. And in Wigner-Weisskopf theory, for example, of spontaneous emission, you get a rate of spontaneous emission. So the entanglement is still there. We're using it to get dissipation and noise at 0 temperature. Okay. Now, I don't know whether you'll be talking about learning at all, Natalia, but here's an example of a continuous time version of a Boolean agent. And I've deliberately written it in a form inspired by neuroscience. So it works like this. Here's our agent, an irreversible, far from equilibrium device with access to a large amount of free energy. It acts on the world by doing work, and the world responds a bit like a function oracle and produces a sensation in the agent. Simultaneously, the agent sends a copy of the work signal to a physical neural network, which tries to predict what the agent should see coming back from the world, and compares it here to produce an error signal, which it then feeds back onto the physical configuration of the neural network. It's just like sheep and goats, but done with electronic signals. It's dissipative, it generates heat, it's highly stochastic, and here's how it works. First of all, we need to ask what the error signal is. So let me just go back and introduce a couple of key things. There's the actual action that goes to the world, I sub A of t, and the signal that comes back from the world, you can think of it as the output of an oracle, but the neural network is generating this IS tilde, which is a prediction of that. They're not necessarily the same. So the error has to compare the actual signals coming from the world with the predicted sensation and compute an error signal, which is just this mean square time average. If these are currents, this is obviously energy dissipated. And so the energy gets dissipated here in this comparator as well as in the actual machine during the switching. Okay, so if I normalize the power in the signal in the sensation signal coming from the world and the predicted sensation signal, just to make it easier, I get this nice expression for the error signal, which you see depends on essentially a convolution of the prediction and the actual sensor signal coming from the world suitably time averaged. And if I normalize the signals, when these two things become identical, this turns out to become 1 overall, and the error goes to 0 with the normalization that I'm using. Now what we really want to know is how to change the weight, so we take the derivative of the error signal as a function of the weights. Just assume there's only one weight for the moment. I get this expression, and you just churn through and you find we now need to ask, how does the prediction correspond to the actual action of the agent? So I'll choose this tanh function. And this beta is some real positive parameter related to temperature. And so now I can put it all together, work out what the weight, what the change in the error is as a function of the labels of the data, which is coming from the world. The labels on the data is coming back from the world. The data, and I get this derivative of tanh function, which is sesh squared. I've made an assumption about timescales here just to carry through the integrals a little bit more easily. And then we now need to ask what the weights are doing. So what we do, we imagine that in the absence of any feedback, the weights is just an Ornstein-Uhlenbeck thermal process subject to some dissipation, so they'll settle into a big Gaussian distribution. As soon as we apply the feedback, we generate this highly multiplicative, this highly nonlinear drift term. This is the dissipation and the diffusion coming from the background of the rates. It's not too matter, don't worry too much about the definition here, but this is the learning rate. It's the product of the feedback strength and the temperature of the diffusion process. But if it's a NOT gate, then the product of the true action and the true sensation is just -1, so let's just do that. And then I get this very, well, it looks simple to me, but maybe it doesn't to you, this simple one-dimensional Ito stochastic differential equation where this I tilde S of t is a function of IA of t. So IA of t, which is the action, enters in two places, and then the feedback is being changed according to the rule on the previous slide. So you can simply solve this for the weights, and you show that if I start off with an initial Gaussian distribution, as it begins to learn, the weights all converge on roughly a single point about which they fluctuate. So the weights are being cooled by the learning process. If you do it in the Fokker-Planck description, you start off with this broad Gaussian distribution of weights, but as it learns the NOT gate, the entropy is reduced and the weights all begin to pile up and become concentrated on some positive value in this sense. So here we see explicitly in a stochastic model how learning a stochastic control leads to entropy reduction and heat generation in these models. Okay, so that's the classical case. And if you want to just keep it in mind, just remember from this point of view, in a physical learning machine, not an algorithmic learning machine, it's something different. In a physical learning machine, cooling in weight space is the same as learning. But in some very complicated thing, the weight space could be 1 billion or 1 trillion parameters. It could be absolutely enormously high dimensional. But somehow or other, it's got to be cooled down to particular attractors in this very high dimensional space by dissipating energy. And once it's there, it has essentially learnt the function. In this case, it's an unknown function imposed by the world. And it can now predict what will happen for that particular function in the world. So this is one example of how this would work in Natalia's experiment in Oxford based on a single electron tunneling in quantum dots. It's a very simple, well, actually, to a theoretician, it's a simple device, not so simple to Natalia perhaps. But there's a single electron tunneling process through the quantum dot, and up here is a charge sensor, which essentially acts like a sort of field effect transistor. When this is occupied here, it changes the electrostatic potential on the dot and pinches off conductance through here, so we get this kind of stochastic stepwise switching depending on whether the dot is occupied or not. So now if I monitor this current and feed back onto the tunnel gates and the plunger gate for the energy, I can set up exactly that sort of stochastic control protocol I just described. For NOT. NOT's not very exciting. There are 4 1-qubit gates. 2 of them are constant, always on or always off, not very interesting. There's the identity gate, which just reproduces the input, the output, and the NOT gate. The next one up would be a 2-qubit gate, like XOR, and for that we know we need a neural network with at least one hidden layer with 2 perceptrons coupled to a single output perceptron, and so we need of the order of 8 or 9, 1, 2, 3, 1, well, I've forgotten. Anyway, of the order of 10 weights in order to train it. So even in going to a single binary gate of 2 inputs, it's already gone to a 10-dimensional weight space. They get pretty complicated fast. Right, now I want to switch in the last part of the talk to how to do this in the quantum case, keeping the essential features of dissipation, now coming from quantum noise like spontaneous emission. So the model I'm going to focus on is a fairly famous model from quantum chemistry called the Jahn-Teller model, or the conical intersection, which is one of the foundation models for electron transfer in molecules, where the motion of the nuclei in the molecule are critical in determining whether or not an electron can tunnel from one part of the molecule to another. So this really simple model was devised many years ago based on a single qubit and a single harmonic oscillator degree of freedom to represent the nuclear coordinate. In quantum optics, it would represent the field in a cavity, perhaps a microwave cavity. And then we have this spin boson type coupling between the displacement of the harmonic oscillator and the sigma z, Pauli sigma z of the qubit. So if you think about if the qubit's in the ground state, this is a bias one way, it's just a linear potential, biases it one way. If the qubit's in the other state, it biases it in the other direction. So this is like a quantum controlled bias of a quadratic potential, not very nonlinear in this case, but as you'll see in a minute, it's intrinsically nonlinear. And so this is a state-dependent bias force of the kind that are used in ion traps for ion trap quantum computing and so on. It has a parity symmetry. When x goes to minus x and I do a pi rotation around the x-axis, everything stays the same. And so there's a simple parity symmetry in this model which enforces a particular structure to the spectrum. Now, I'm going to operate in a regime where the oscillator coordinate is slow, and classically you would use this adiabatic potential where the qubit is essentially slave to a slow-moving oscillator coordinate, and you effectively get these two potentials. One comes from having a quadratic potential displaced to the left, the other from a quadratic potential displaced to the right, and where they cross, there's a splitting due to the omega, the bias term in the Hamiltonian. That leads to a splitting. And this omega, which in a quantum optics model would be a Rabi frequency, is entirely controllable. And so I'll use omega as the control parameter to insert the weights to make this a trainable device. So anyway, I get this potential. You see straight away that the ground state manifold is a double well. But there's a key quantum feature here, which is due to a topological phase, a Berry phase, and that is there's a change in the qubit structure of the state. Have I got it around? Oh, I've swapped them. It should change from minus to plus as it goes through this. Oh, yes, it does. It goes from plus to minus. So instead of a single particle tunneling in the potential, the qubit state also undergoes a transition as it goes from left to right. So instead of actually measuring the position, if you like, of the particle, I can simply do a readout of the qubit. And this won't happen in a quantum version of a double well. This is a purely topological feature. So it's pretty easy to work out where the degenerate minima are. They depend on something called the Jahn-Teller energy, which is the square of the coupling between the oscillator and the qubit, divided by the oscillator frequency. Whenever that is bigger than the splitting term, we get this double well structure. And then the splitting of the ground state and the first excited state, the ground state is actually antisymmetric in this case because of the Berry phase. It has the usual exponential suppression of tunneling as I increase the driving, as I increase the separation between the wells. Okay, all of that's perfectly coherent. I haven't put in any noise at this stage. So now let me treat the motion of the particle as classical and just add noise to the classical particle. Then I just get two Langevin equations, one for the upper surface and one for the lower surface. Let's focus on the lower one, which is the double well. And I just write down a Langevin equation and assume it's highly damped, overdamped, with thermal noise, just as I did before for the simple double well. It turns out there's an effect of mass because there's a slight renormalization of the curvature around the minima, and so that's given by 1 on 2 omega, where that's the oscillator frequency. Now, it's easy to work out the tunneling rate. It goes back to Kramer's years and years ago for weak phonon damping. I'm already anticipating a quantum picture, but classically, of course, there are no phonons, it's just vibrations. And you can work out Kramer's rate for first passage. That's the the typical rate or the inverse of the first passage time taken to go from localization in one well to localization in the other well, and it has the usual exponential suppression. And notice there's this inverse temperature, kBT, coming in here. And the barrier height is purely a function of the bias, the Rabi frequency driving this device, and the temperature is, of course, controlled by the environment. Oh, wrong way. What's going on? Oh, it's that one. So it turns out there's an optimal barrier height for which the transition rate saturates at a temperature-independent value of the dissipation rate eta over omega and E. Just goes for the just whatever E is, 2.7 or whatever it is. So at optimal bias, no additional energy is wasted, and the transition occurs at minimal thermodynamic cost. It just tunnels through the barrier and the energy doesn't change because the bottom of the wells never change. It's the tunnel barrier which is being modulated in the Yarn-Teller model. But due to the Berry phase, the qubit state does indeed change, oh that should be Z, from plus Z to minus Z with the same energy. So a qubit measurement would in this case signify the transition, and if I wanted to build up multiple perceptrons, I'd just put them end to end so the qubits could couple to each other. But let's just stick with one. Okay, so now let's put in damping for the quantum case. So now let's go purely to quantum and assume zero temperature and put in qubit damping, just spontaneous emission, and leave this bosonic damping at the same rate eta, but now into a zero temperature heat bath. And then thermal activation is completely suppressed, but quantum fluctuations will now drive the transitions through spontaneous emission. Again, we can work out the tunneling rates. They don't change, although now it's dissipative quantum tunneling. The role of tunneling, and this is a Landau-Zener transition because the electron flips its state as it goes across the device. The role of dissipation now is not to change the tunneling frequency, but to decohere the device or decohere the quantum states in the right basis. So without decoherence, tunneling would produce a cat state with the particle located in the left barrier, the left of the barrier and to the right of the barrier, and the qubit would also be entangled with the motional degree of freedom. But when I put in dissipation, I get decoherence, and it's easy to calculate the decoherence because it's trying to produce a cat state separated by 2x naught, and we know exactly how to do that by looking at the left-to-right coherence. It decays as the damping rate times the square of the separation of the cat state. Likewise for the qubit, this takes a bit more calculation, but you can show as far as the qubit is concerned, the fluctuations coming from the combination of spontaneous emission and the decoherence in position looks just like a position measurement due to the underlying qubit. So what it's adding is essentially a dephasing term to the qubit at this particular rate here, which in the limit of large gamma is just 4 kappa squared on gamma squared. Okay, so now we have the picture. Low temperature, very low temperature, it can undergo quantum tunneling, but the decoherence coming from spontaneous emission and from oscillator damping causes it to become localized stochastically in one well or the other. And so the total decoherence rate is the sum of those two things, depending on the separation between the two minima. And we very quickly discover that the quantum analog of Kramer's rate leads to a crossover between a classical and quantum regime that depends upon some, hang on, wait a minute. Yes, it depends on a critical temperature. So now as you cool the system down, you see the Kramer's rate gradually give way to this true quantum tunneling. And below this critical temperature, we just see decoherence-induced localization of the qubit. So this is what it looks like. Here's the classical Kramers for given values of omegas and deltas and so on. As you decrease the temperature, the fluctuations due to the classical go to 0, but the quantum always stays the same, so we get this crossover regime as we go from the classical Kramer's activation, thermal activation, to this quantum decoherence activation. So this is a true quantum perceptron. It's dissipative. So now we can do a little bit of work on the thermodynamics of this. We treat it just as a two-level system, located on the left or located on the right. And we simply work out what the probability of the system being found in the left well or the right well is, because we know the decoherence rates. And it turns out not to be a sigmoidal function, but something that's not very different from the sigmoidal function. Because if x naught squared is very large and positive, this goes to 0. If it's very large and negative, this goes to 1. And so it's basically a quantum activation function for this quantum perceptron. The effective computational temperature, however, is not kT. If you think of the computational temperature as something that determines the probability for switching in the sigmoidal, in this case it's determined entirely by the tunnel splitting, not temperature. And so in other words, in this device, there's an optimal sigmoid gain operating point determined not by the temperature, but by the quantum tunneling. And as soon as you combine that with, let me just move on to the next slide. Combine that with all the other features in the model, you can come up with a comparison of the classical case to the quantum case. So in the classical case, the switching mechanism is thermal. In the quantum case, it's tunneling. Blah, 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 blah. Let me come down to the Landauer cost per qubit. In the classical case, it's kBt log 2. In the quantum case, it's 2 delta naught, which is the quantum tunneling gap. So the quantum analog of the Landauer cost is not kBt log 2. It depends entirely on this coherent quantum tunneling feature in the model, at least for this model. So summarizing everything, if you were to put this into a learning algorithm and say, let's do the feedback on the classical perceptron and the quantum perceptron, sample over many epochs and try and reduce the error, the mean square error, you discover that the energy dissipated per step of epoch goes as kT times the change in the error per epoch. So as the change in the error gets smaller and smaller and smaller, the energy dissipated per epoch gets smaller and smaller and smaller. In the quantum case, that is replaced by h bar times mu, a dissipative quantum tunneling rate, but the information theoretical component of this stays the same. It's just the change in the average error per training epoch. So this is a kind of generalized Landauer principle for training quantum neural networks, at least quantum neural networks configured in this fashion. Now, from the point of view of technology, it turns out that typically that tunneling frequency can be made very small compared to kT. Of course, you can make kT small as well, but at a huge expense. But the tunneling can be made smaller and smaller and smaller. And so quantum learning machines should be thermodynamically more efficient than classical learning machines, as well as having all the other advantages of quantum learning, which is new kinds of probability distributions and more efficient ways of generating transformations over probabilities. How could you do this? Well, this recent experiment by Wiesel et al. Using trapped ion quantum simulation literally found a way to simulate this Jahn-Teller effect. They call it electron transfer in a molecular system. They changed the temperature, not by a cryostat, but by using sympathetic cooling in an ion trap. You can take another isotope of ytterbium and use different transitions to sympathetically cool the active one. So I can easily enter this quantum domain as they showed, and they put in exactly the same sorts of damping, except they left the thermal temperature. And they had completely independent control over every parameter in the model, including the damping rates. And so they were able to show that it does behave the way I've just described. The reason that the thermodynamics of ion traps are very favorable is because we don't need a fridge, at least you actually probably do, really, if you want to do quantum computing. But at the very least, the cooling of the ions themselves is done via optical pumping, and the optical pumping requires a laser, which is a very low entropy source of work in the system, and it dumps the energy out into a very, very low temperature environment, which is the radiation field at optical frequencies. So this means you can tune right through to this adiabatic, strongly quantum domain with optical pumping as a state preparation. The other way to do it is to use optomechanics. This is something I've been working on a lot with people at Sussex. Here we have waveguides. This is a ring resonator for light, which can have clockwise and counter-propagating, and you couple the light in through here. Then we have these mechanical resonator bars, and the radiation pressure force here means the number of photons here exerts a force on the mechanics. So this is just number of photons times x. And this is sufficient. If you excite it with single photon pulses, it's equivalent to having a qubit interacting with a harmonic oscillator, just like the Yarn Teller model. Except now things with optical frequencies. You will need cryostats and so on for the mechanical part. But the nice thing about having the mechanics there is it provides a wonderful way to prepare the mechanical system and measure the mechanical system by putting an RF signal through the conductor on the mechanics. And then we can use single photon pulses with Raman control to excite single photons in the cavity. So in this case, we send in a single photon pulse with a Raman control pulse. It excites a photon in the cavity, which pushes on the mechanics, and you can detect it through the mechanics. If I don't send in the single photon pulse, this will essentially, and I excite the mechanics, this will extract a photon from the cavity. So this will be a single photon source and a single photon detector. So it looks pretty clear that these devices can be built, but if, in the case of learning, we've got to ask ourselves, can they be trained? And this is a whole other story, which I haven't got time to go into. Lots of people are looking at it for the case of stochastic perceptrons. This is some work I did with my colleagues at Sussex and my collaborators at University of New South Wales. There is a way to train single electron, single photon stochastic physical neural networks. It looks very much like cooling, as I described before. And there's this beautiful model from Peter McMahon's group in Cornell called TRON, which is a bit dated. But anyway, it's a trainable architecture for random optical neural networks. And the nice thing about optics is photons are cheap to produce, relatively speaking, and they're coming at you at a huge rate, and they have very, very little energy. Of course, if you use coherent pulses, this won't work. You can't use coherent pulses with, on average, one photon, because there'll be no entanglement generated. It has to be Fock state pulses. So to conclude, quantum machine learning, thought about in this fashion, offers a different class of controllable, learnable probability distributions. And I've shown you that there is a way to do this that's thermodynamically very favorable, as well as having some quantum advantage. Let me just conclude by acknowledging my collaborators. Sahaba Sirius Fahani in Bristol, Matt Woolley at UNSW, in Canberra, actually, UNSW in Canberra. Josh Burns, a PhD student with me at the University of Sussex, working on the single photon work. Natalia, of course, we all know. Federico, we know. And Parth Gerard is a postdoc in Natalia's lab. Thank you very much.
Thank you, Gerard. But what was like?
Hello. Yeah, you can hear me?
Yes.
Yeah, so one of the aspects of learning is also the differentiability of the activation function, and that would restrict the class of dissipative dynamics that you could do. Do you think that's the case?
Certainly, yes. I've just considered the simplest kind of dissipation into a zero temperature heat bath. You can engineer reservoirs to get more interesting dissipation. For example, if I use a squeeze bath, I could generate a much more phase-dependent form of damping. I haven't investigated that, but there's always the possibility of putting in another quantum object between your system of interest and the bath and using that to control the damping, like sort of Kondo effect dynamics. So in the long run, no, I don't think it necessarily restricts it to one particular kind of damping. The kind of damping you use will lead to a decoherence in one basis or another, and so it sort of depends a bit on how you were going to encode your information in the perceptron, how you want the decoherence to occur. And so it may be that if you have some unusual way of encoding the information, you need to build a decoherence channel that has exactly the right properties. But I don't think in the long run that's a problem. It's an engineering problem, but I don't think it's fundamental.
Okay, thank you.
Thank you for the talk. I have a pretty basic question. I think it's related to the fact that learning dissipates, you said. So first I would like to check if that's the reason. So you say this, is it because the mapping between the input and the output, it's an irreversible logical process, and so that's why it dissipates? Is it more or less the...
No.
No? So can you explain?
Okay, let me put this differently. Let's suppose you're going out into the world and you want to learn effective strategies. One way is just to memorize every single thing that happens, right? Every time I do something, a rock falls on me, so I remember, okay, don't push on that part of the wall or whatever. And gradually, as you go through life, you're getting this huge memory of storing how the world reacts to my actions. You get to the point where you just can't search it. It takes forever to search it, and you need more and more space to store it. A far better strategy is to learn the correlations in the data and just store those, and then erase most of the memory and pay the Landau erasure cost. So that's the other way to see why learning, which compresses information, necessarily has to dissipate energy, because it is compression.
Okay, so it's because we erase data. It's that's
Exactly.
at the end of the day, this is an erasure of the stuff we learned in our memory, because now we learned it, so we don't need to memorize it
Essentially,
again.
yeah.
Okay.
That's a crude way to put it, but that's the basic message. Yeah.
Thank you.
So, hi there. So thanks a lot for a splendid keynote. I was intrigued by your statement, I think it was slide 22, when you said that you need a finite amount of noise for the systems to learn, both classical and quantum. I was wondering whether you think that's an indication of the system exhibiting the so-called stochastic resonance, which is very well understood in information theory, in neuroscience, even in climate systems, in very large-scale nonlinear dynamical systems, whereby a controlled amount of fluctuation enhances the system ability to process information and compute.
It's absolutely right. Stochastic resonance is a way of amplifying weak signals. And where it takes a functional role in learning is not so much in these devices, but in so-called spiking neural networks. Stochastic resonance is very useful to enable synchronization of spiking neural networks. In fact, stochastic resonance was discovered in a neural network in the giant squid back whenever. So you're absolutely right, and it plays a critical role in spiking neural networks.
Thanks a lot.
So thank you very much for this very nice talk. So we were trying to implement something similar in a commercially available computer like IBM, but we encountered this problem that error channels that are typically not significant for other tasks are very significant because they are attacking trotterization. They are not commuting with the Hamiltonian we are trying. Do you know any way that is quantum efficient that can skip the trotterization?
Okay, that's an extremely important question. So when I say that learning, noise is essential for learning, it's not any noise is essential for learning. It turns out you have to carefully engineer the noise just right. And Natalia's been thinking about these things by sending in microwaves to control the temperature. And you see there is an optimal noise level. So it will now come down to the details of how you're trying to do the, what is the physical device that's forming your quantum switch? And indeed, not all noise is good, and you have to be able to engineer it and tune it in just the right way. So that's all I can say at this stage without looking at particular models.
Thank you for the talk. So I do agree that learning is a physical process. This extends the ideas that computation is a physical process. But then there are two components here, is the working at the physical laws of nature and designing our abstract models that intend to capture that, albeit subject to limitations. In what you presented, I'm not sure quantum machine learning or quantum aspects of learning fully justify itself. I think this is a relevant question for classical learning as is. So I don't see how quantum learning completes this picture.
Okay, well, fair enough. So the reason I wanted to look at the quantum case is because in any classical device, we always have to ask ourselves, what happens at low temperature? And so quantum happens at low temperature. And so if you don't know how to calculate what happens at low temperature, call it quantum, call it whatever you like, you don't fully understand the problem. And so one way to think about why it's quantum is I want to know how this operates at low temperature because I want to optimize its thermodynamic usage. Now there is this sort of philosophical thing running in the background here of what is the difference between an algorithm and the hardware. I would say algorithms, when they're presented to students in computer science, not that I've ever done a course in computer science, seem totally divorced from hardware. But there is no example of an algorithm which is actually divorced from hardware. Going back to Babbage's machine, which is certainly not a digital computer, it forms a kind of computer called the integer register computer, which is like the abacus. And it's a Turing universal way of doing computation, worked out in the 60s by Minsky and others. And it forms the core of mechanical calculators used in the 18th and 19th century. So if all you have access to is mechanical devices, then you have a completely different way of thinking about how to do algorithms. Likewise, if you want to calculate the value of pi, and all I give you is a bit of string and lots of sand, you're not going to try and, well, you could, I suppose, you had enough sand, build a silicon computer out of it, but a far better strategy is just to make a circle, inscribe a quadrant on the circle with a square, and start throwing sand into it, and then just measure the amount that lands in the circle and divide that into the amount that lands in the quadrant, and this will approximate pi. It's the standard Monte Carlo algorithm for calculating pi. So algorithms are never independent of hardware, and this is an acute lesson from Shor's algorithm. Shor's algorithms make no sense in the classical world. It's just crazy. But in the quantum world, we know there are efficient algorithms for factoring. Whether you think that's interesting or not, it's another matter. So what I'm trying to say is my philosophical bias, you may disagree, is that it's impossible to consider algorithms independently of the hardware on which they're realized. If you like, we can talk after.
Yes,
I'd be happy to discuss it further because it is a contentious point, I would agree. Yeah.
Nice talk, of course, Gerard. Following up the first question, can you make a difference between inferences and training in the approach? That's one question, which is very broad because it depends on a lot of factors. And the second one is when you make the comparison between the fundamental bounds between classical and quantum training, I would say, what happens if you take it in a fully burdened way when you account for all the classical costs to drive the qubits in the case of photons here? So okay. is it creating a difference, further difference, a lower difference between the classical and quantum? Yeah, that always matters.
So if you need to go back to the PowerPoint, you really need to do that. If there's a dilution fridge involved, it's going to be expensive. There seems to be this conservation of expensiveness somewhere or other in building these machines. If you use quantum optics, atom optics, and ion traps, the cooling is typically done by optical pumping, which is incredibly efficient thermodynamically. But there's a price to pay there too, because you've got to engineer the devices and move the atoms around and all the rest of it. Then you need control circuits to put the switches onto the device. Those control circuits are analog to digital converters, very complicated things. There's dissipating power. So yeah, you really do have to work right up through the whole stack to understand what the thermodynamic cost is. But I'm pretty confident that the way we're doing it in machine learning at the moment is definitely not the optimal way to do it. After all, the world is full of learning machines, billions of them. There's a few here, I hope. And they operate on 20 watts. The human brain dissipates 20 watts. Now, you could argue that the training cost, as you referred to before, hasn't been taken into account because the training cost is evolution. It's squandered, I don't know, trillions and trillions of watts in energy and eliminating just about every organism before it gets to us. Now, your question about training versus inference is an important one. Training will always be more expensive than inference. So what happens once it's trained is the energy dissipated per epoch in the inference cycle would be the minimum. And so when you put in the numbers, you could simply say that the change in free energy at each inference step is a minimum, which is the kind of technical justification behind Carl Friston's ideas on the free energy principle.
So it means the difference between classical and quantum is going to be more important in training than inferences? In most qubit modalities or not?
Yes, yes, definitely, because training is where you pay the biggest cost, because that's where the compression is first taking place.
Yeah. Thanks.
Last question.
Thank you very much for the talk. I have a quick question about quantum and classical training. What are the difference in terms of energy scales? Like how much quantum training is efficient more than classical one?
Yeah, it goes back to this formula here. This is the average change in energy per training epoch for a change in the average error. So there's a cost function. So this is as a physical thing on one side and an information theoretical thing on the other. The information theoretical thing is a cross entropy or Kullback-Leibler divergence, or in the simplest case I've done here, just a mean square error. So you want to make this as small as possible in training. And so eventually this delta E goes down as delta E goes down. The error goes down, the energy cost goes down. But you're stuck with this coefficient out the front here of KBT. And the key point in the quantum case, KBT gets replaced by h bar mu, where mu is a tunneling rate. And in principle, mu can be that should be h bar mu is much, much less than KBT. Not always, but in principle. So training in the quantum device should be cheaper than in the classical device at low temperature. So the question is, how do I get low temperature? Well, in optics, it's not so bad. In superconducting devices, it's not so easy.
Okay, so I think we can finish and thank again Gerard for